Welcome to another coding tutorial, and in today's video I'm going to show you how to create this cute bouncy sketch. I actually made this sketch as part of the announcement of the Processing Foundation's Back to School fundraiser, and I have a little bit of news to share with you. I recently joined them as their interim manager of communications. It feels a little bit like a full circle moment because processing and p5.js were one of my first entries into this world of creative coding. I guess this is my way of telling you that I might be popping up in a few new ways. I'm really excited to share with you this tutorial because my matter.js videos are actually one of your favorites, and obviously using a physics library has a lot of the perks. One being that you get to enjoy the results without really doing the hard lifting work. But if you want to peek a little behind the scene and get a better understanding of how the little pieces work together, this might be a video for you. Another video that I recommend you check out is this one by Dan, where he walks through the fundamentals of motion. We use a slightly different technique in figuring out the collision detection. He uses the elastic collision equation in 1D derived from conservation of momentum and kinetic energy, while I'll be using the rigid body impulse resolution technique, which works in 2D and is the same approach used in many game engines and physics libraries like matter.js. Alright, so here's how we're going to approach this. We're going to approach it in 3 steps. First, we're going to check if the balls collide, and then we're going to correct their positions to prevent overlap. And then third, we're going to calculate the new velocities to create that bouncy action. Let's start with the first step. Imagine that there are 2 balls, let's call them ball A and ball B, and when they get close enough to each other, they collide. To check if they actually collide, we measure whether the distance between their centers is less than the sum of their radii. If it is, collision is happening. In the second step, if a collision happens, we then correct their position so that they don't overlap. We do this by moving each ball half of the overlapping distance along the collision normal. This is the line connecting their centers. This is done so that we make sure that they're pushed away from each other equally, preventing them from sinking into one another. And once we correct their position, we now want to figure out the new velocity so that they bounce off each other realistically. To do this, first we need to check whether they are actually moving towards each other. Imagine that you're ball A and you want to know how ball B is moving relative to you. To figure this out, we calculate the relative velocity by subtracting the 2 velocities like this. Relative velocity equals to the velocity of ball B minus the velocity of ball A. And by subtracting it this way, it is a vector that points from A to B. The direction is very important because it tells you how B's motion looks from A's point of view, and if we did the opposite way, A minus B, the vector would point in the opposite way and our check for approaching each other would be flipped. Next, we project the relative velocity onto the collision normal using a dot product. Basically how fast the balls are moving towards or away from each other along the line that connect their centers. The dot product tells us how much of the relative velocity is moving along that line, and once we do the calculation, if the sign is negative, it means that the relative velocity is pointing in the opposite direction as the collision normal. And this basically means that the 2 balls are moving towards each other. And if the signs are positive or 0, then they're not approaching each other, and so we do nothing. In a case where the sign is negative, we use an impulse to update velocities. The impulse basically is this small change in momentum, or this quick bounce between the balls that changes their speed and gives us that bouncy look. It depends on 3 things. First, how fast the balls are approaching each other. Second, their masses. And third, the restitution, which is how bouncy we want the collision to be. And the formula looks like this. And then we update the velocities on the 2 balls, and that's it. I'm going to be using the 2.0 version because we'll be playing around with some typography at the end, and you can change the version by coming to this button here, and then you can change the version here. And I'm gonna do 2.0.4, which is the latest one. All right, and as you can see here, there's a new private sketch features which you can switch between public and private here. All right, let's get started. First, we're going to declare a few variables for the position, the velocity, and the acceleration of the ball. So let's declare those: position, velocity, and acceleration. And these, I'm going to create them as vectors, which is an object that can hold 2 to 3 values, and I'm going to use them to hold 2 values, x and y. And so position will be equal to create vector, right? And we're going to put in x and y, which I guess we can declare them as, how about, let's put x in the middle of the canvas, and then how about y at 0. Okay, and let's just maybe draw them out as an ellipse. So we're going to do pose.x and then pose.y. And then for the radius, I'm going to actually also declare it as a variable. How about we do 50? And then we're going to do r times 2. And because the width and the height, it's a circle, I'm going to just put in one argument here. And let's click run. All right, so now we have a circle. You can see only half because y is at 0. Now I want it to move down. So we're going to change the velocity. So let's do vel equals to create vector. How about I just have it move down, so the x component will be 0 and then the y component will be 1. And then to update the position, what we need to do is inside draw, we're going to put pose.add, and then we're going to add in the velocity. And this is how we can add two vectors together. And then now the ball is moving downward, right? And it is moving downward at, let's see, print pose.y, 1 pixel at a time, right? Per frame. Great. Next, what we're going to do is we're going to create the velocity. So basically, we can add different kinds of forces, but what I'm going to do is that I'm just going to add gravity. So that is also in the y component. So acceleration is the rate of change of velocity. So let's say that I put in 0, and I'm actually going to create it as a global variable here, gravity. Let's set it to 0.1. Now I'm going to actually set velocity initially at 0, and then we're going to add the acceleration to the velocity. So the speed is going to be changed by this amount, and then the position is going to be changed by the velocity. So you will see in the change in the position here. All right. It's kind of hard to see from the numbers, but you can see that now it doesn't change just 1 pixel at a time, right? The rate of change is different now in every frame. So as you can see here, the ball is moving down faster. If I change the gravity to, let's do 1, it speeds up as it comes down. All right, so now let's put this inside a class. We're going to come to this arrow here, click the plus sign, and then click create file. Let's call it ball.js, add file. Then before we start writing a class, let's go to index.html and then copy this line of code, and we're going to change the name to ball.js, and now the file is integrated into the program. Let's go back to ball.js. Okay, so we're going to start by writing a class. Let's call it ball. And then inside the constructor function, I'm going to go back to Sketch. We're going to put in basically all of these, and also radius. So I can delete this. Okay. So we can delete x and y too, I guess, because x and y, I'm going to use it as parameters. And we just put it in here. And then we need to make sure that we put this dot on all of this. This dot, and this dot. Okay, the two methods that we're going to write are update and display. Okay, and now we're going to copy these into the class. So for update, it's these two, right? And then display. And we don't need print. Can I delete this and then add all the this dot. All right. Oh, and let's put r as another parameter here too. Okay, let's go back. Now, how about we create a ball. Let's call it ball A. And ball A is going to be a new ball. Let's put it, how about we randomize it? Random between 0 and width divided by 2. And then for height, let's do random between, I want it to start a little bit off the screen from the top, so maybe -300 and -100. And then for the radius, I'm going to set it randomized between 30 and 70. Okay, and then inside draw, we're going to do ball A dot update and ball B dot display. Okay. Run. Oh, there's no ball B, ball A. Okay, now as you can see, the ball moves off the screen. So how about we write a method called bounds? And basically, we're going to use this to check the boundary to make sure that it stays inside. We're going to write a conditional statement that says if this dot post dot y, right, plus this dot post dot r, which is the bottom part of the circle, right, because this is the center, is greater or equals to height, then we're going to set the position to be equals to height minus this dot post dot r. Oh, and then we want to call this bounds function, and we can do it here. This dot bounds. Okay, didn't work. Oh, this dot r. No post. Okay. All right. Great. Now let's work on the rest of the side. So else if this dot post dot y minus this dot r is less than or equal to 0, then this dot post dot y is equals to this dot r. And same thing for the x component. So this dot post dot x plus this dot r is greater or equals to width, then this dot post dot x will be equals to width minus this dot r. Else if this dot post dot x minus this dot r is less than or equals to 0, then this dot post dot x equals to this dot r. And it will be kind of hard to see right now because it's just falling down. So what I'm going to do is I'm going to actually start the velocity with a random vector. And we can do that by using this function p5.vector.random2d. And this will actually give us a random vector of magnitude 1. And so what we want to do is we also want to multiply it by a scalar value. How about we do it randomly between what? 2 and 4. This is just my check to let's not put gravity. Let's put gravity at, acceleration at 0. Actually, what we can do is we just do this. It's not bouncing off. Okay. Totally missed it. So in the bounce function, now we basically say that once it hits one of these sides, make sure that you just basically set the position to be on that side. And as you can see, that's what is happening right now. Once it hits, then it's stuck right at this position that you see here. So now what we want to also do is make sure that the velocity is flipped so that now it bounces off of these corners, these bounds. So what we're going to do is that we're going to set velocity. So for the y component, it will just be this dot vel dot y times equals to, And I'm actually going to set it to the opposite of a value we call restitution, which is how bouncy we want these collision to be. And this is also going to be the constant that we use to actually bounce the two balls. So restitution, and actually let's just set it first. So gravity is 0.3, restitution is, how about we do 0.5. Okay, and I'm going to copy and paste it here, and this will be x, this will be x. Right, boop, boop, boop. It's kind of slow. Why is it so slow? Maybe we do 4/10. You get the point. All right. Okay, so now I'm going to actually comment this out and bring back what we had before. So it's like bouncing, right? And if you change the restitution, let's do 1, you can see that the floor becomes a lot more bouncy, right? So you can play around with these values. So I'm going to set it at 0.5 for now. And now that we created this class, let's create another ball, and then we can work on the collision detection. Okay, so ball A and ball B, and we'll be ball A, okay? Okay, so ball B, we're going to just copy and paste how we create ball A here. And, okay, and also copy and paste this, ball B. All right, run. And as you can see, they basically overlap and nothing happens because we have not written a collision detection function. So that's exactly what we're gonna do. Function, let's call it collide. Okay, remember we're ball A and the other ball is ball B. So the 3 steps that we're gonna do. First, we're going to check if they overlap, like what you see here. And we do that by checking if the distance between their centers is less than the sum of their radii. So we're going to create, how about I call it dist AB? Yeah. And I want to get the vector between the 2 centers in the direction that is from point A, from ball A pointing to ball B. And to do that, we can subtract the 2 vectors, the 2 position vectors. So p5.vector.sub. And if we want to point from ball A to ball B, we need to put in ball B first, ball B.pose and ball A.pose. And this will get us a vector that points from ball A, position of ball A, to position of ball B. Okay, and then we're going to next get the magnitude of this. So let's just call it dist AB mag, and we can just do dist AB dot mag. Okay, and then to check if they overlap, we also need to know the minimum distance, right? And the minimum distance such that they don't overlap is the sum of their radii. So ball A dot R plus ball B dot R. And then the conditional statement would be if what? If the minimum distance is greater than dist AB mag, right? Okay, I want to do the other way around. If it's less than, right? So if the minimum distance, if the distance between AB magnitude, the line between their centers, is less than the distance between the sum of their radii, then we're gonna say, what are we gonna say? We're gonna print collide. Else print not collide. And I'm actually gonna go back here real quick and then I'm going to actually randomize this so that they move around a little bit. And let's do this as 2 and 4 again and keep gravity. Okay, let's try it. Oh, did not print anything out. What did we do wrong? Oh, we never called it. So let's call it before we update and display. Collide, save, run. Not collide, not collide. Collide, not collide. It works. Okay, next what we're gonna do is, we don't need this else here. So once we know that they collide, then it comes the second step, which is we need to correct their positions, right? To correct their position, what we want to do is we want to first know how much they overlap. So we're gonna create a variable called overlap, and how much they overlap will be what? Min distant, right? Minus dist AB mac. That's how much they overlap. And now we want to move them out from away from each other by half of that amount, right? Half one way, half the other way. And so we need to know what is that direction that we need to move it. And basically that direction is the same direction as the dist AB vector, right? Because dist AB is already a vector that points from center A to center B. But we're going to actually normalize it, meaning that we're gonna make the magnitude to be 1. We don't need the magnitude, we just need the direction, because the magnitude is overlap here. This is how much we want to split them from each other. So what we're gonna do is we're gonna set n for this normalized vector, the collision normal, and we're gonna set it equals to dist AB, and then I'm just gonna copy it so that we make sure that we don't change this actual vector, and then we're gonna do normalize. Now we're gonna set another variable called correction, and this is, as I told you before, it's going to be a p5 vector, right? That multiplies this magnitude overlap by n. So let's do n comma overlap. And it's not just overlap, it actually is overlap divided by 2, right? Because we're splitting how much, because if you just do overlap, they would go a little bit too far. And now we want to add it and subtract it to the 2 balls. Because the vector that is pointing from A to B, we want to subtract it from A because it has to go in the opposite direction, and then we will add it to B. So it's going to be ball A dot post dot sub, right? We want to subtract by correction, and then ball B dot post dot add correction. Okay, let's see. Run. Okay. Yeah. I wasn't sure in the first one because it still seems like it overlaps a little bit, but maybe...
A few moments later.
I thought it was the rounding error, but I think it's because of the bound, right? As in, it cannot move to the left anymore, so it might just be kind of like moving in and out on each other, and this is how much it can separate. Next, we're going to find the new velocities, and we're going to do that in a few steps. First, we're going to find the relative velocity. So this one is correction. So correcting positions so they don't overlap, and then now finding new velocities. And we're going to do it first by finding a relative velocity. And to do that, let's set a variable called relative vel. It is going to be a new vector, right? So p5.vector, and we're going to find it by subtracting the two velocities. And as I mentioned earlier, it has to be pointing from A to B. So we're going to put in ball.b.vel, comma, ball.a.vel. So if it points from, whatever it points from, that has to be the second argument. And then we're going to find a separation. So finding a relative velocity and a separation velocity. And basically this velocity is the velocity that it's a value that if it's negative, we know that they're approaching each other, right? We're going to project the relative velocity onto the collision normal using a dot product. And to do that just sounds kind of difficult, but we can just do relative vel dot of n. And now we just need to know if this spits out a negative number, then they're approaching each other. And so we're going to write a conditional statement that say if separation vel is less than 0, then how about we print collide, else print not collide. Okay. All right. So basically, if they collide, we want them to bounce. So now we just need to calculate the impulse magnitude that basically going to allow us to find the new velocity and then just move them away from each other. So the three components that I mentioned earlier that we need, the first one is E or restitution, which I'm going to just set it equals to restitution. The second one is the masses of the two objects, of the two balls. So how about I actually inside ball class here, instead of just having radius, I'm going to actually set mass to be equals to the multiplication between the two radius. And this way, the smaller the ball, the lighter the weight, right? And so on. It's not super accurate, but for our purposes, this is more than enough. Let's go back. And so instead of just setting mass, I'm actually going to, because of the equation, the easier way to approach this is to do inverse mass A, which is going to be equals to 1 divided by ball A dot mass, and then let inverse mass B to be equals to 1 divided by ball B dot mass. We'll be using these two variables in a few places. And the last thing that we need is the separation velocity, which we already calculated here. Now we want to find the impulse magnitude, and we can do it by using the equation J equals to minus 1 plus E times separation velocity divided by the sum of inverse mass A and mass B. And then to get the impulse magnitude, we basically need to multiply n, which is the collision normal, by J. And to find the impulse vector for A and B specifically, what we need to do is we need to multiply it by the inverse of the mass. So we're going to multiply impulse, this vector here, by inverse mass A, and same thing for B, p5.vector.mult of impulse inverse mass B. And then now we just need to add these two vectors, add or subtract to the velocity of the two balls. And in terms of direction, it's the same thing as here, where we subtract to A and then we add to B. Ball A dot vel dot sub of impulse A, and then ball B dot vel dot add impulse B. Okay, let's try. right, so as you can see, the overlapping issue that we had earlier no longer exists. Boop. Okay, let's put this collision function into the class, and then we're gonna make a bunch of these balls. Copy and paste is our favorite. Go back to ball, and then inside this class here, we're going to paste this, and we don't need the word function. Okay, so it's not gonna be ball B and ball A, right? We're gonna use a parameter called other for the other ball, and us is going to be this dot. So ball A is this dot, and then ball B will be other. So let's change all the ball B first. Ball B is here.
A few moments later.
Okay, let's go back to Sketch, save. All right, so now we just call ball A dot collide of ball B, and if everything goes according to plan, when we click run, and there you go. Nice. All right, let's make a bunch of these balls. So how about we create an array called balls, and then let's do num of 10, and then here we can actually set x to be equals to this, y to this, and then r to this. And all of these are going to be inside a for loop, right? That goes from 0 to num. All right, and then now we just need to add new balls into the balls array. So I'm actually going to use the push method, and we just do the name of the array, push, and then new ball, x, y, and r. And then now inside the draw loop. So we need to create two separate for loops. So let's start with the easier one, which are these. Now we just need a for loop that goes from I equals to 0 to I less than the length of the ball, right? Balls.length. And then we're just going to call update and display on all of the balls. So balls of I update, balls of I update. Great. But for the collision detection here, we want to use a nested for loop. So let me show you. So it will still go from I equals to 0 to I less than balls.length still. But then I'm going to use another loop. So it's going to be from j equals to I plus 1. We want to make sure that we check the collision between all of the balls. That is not including the one itself, right? And now I just realized that if we have so many balls, it's just going to be really slow. But for our case, it's fine. But now that I think about it, you can actually check out the Quadtree tutorial later if you want to do collision detection in this way, but for a large number of balls or circles. And so that is a technique where you only check collision between just the neighbors instead of every single balls on the screen, and it's going to help you a lot to not crash your program. Once we do this, what we want to do is we'll actually still call ball A to be equals to balls of I, and then ball B to be equals to balls of J. And then we just call the collide method here. Run. Nice. Do you remember in my sketch that I showed you before, you can see that the balls actually kind of like fall off the screen a little bit. And I actually do that by adding a new Boolean variable called sleep. So basically, if the ball is already hitting the bottom, I reset the velocity to be 0, and then But because the acceleration of gravity is still there, when there is a bigger ball or just a ball that is on top of it, it actually pushes it down off the screen. So what we're gonna do is we're going to come here, and then let's call this Boolean variable sleep, set it to true, and we only want to call this if sleep is, no, sorry, sleep should start as false, right? So if this dot sleep is true, is false, then we check all of these. We do everything here. And as you can see, the boundary condition here is also being checked inside if it's not sleeping, right? But what is the condition that I want to set to make it go to sleep? So if this dot position dot y plus this dot r is greater or equals to height, and this dot, no, absolute value of this dot position dot y is less than 0.5, and absolute value of this dot position dot x is less than 0. Let's say 1. Basically, if it's already at the bottom, right, sitting at the floor, and the velocity is very small, basically like it just reaches the bottom already, then I want to set this dot sleep to be true. But what I also want to do next is I also want to, let's put it before, set the velocity to be 0. And lastly, make sure that the position is at height minus this dot r. Okay, so now what I'm gonna do is, instead of creating these initially, I'm actually going to start at 1, and then I'm gonna create a mouse pressed function that basically adds this, but not at random location. I want to add it at mouse x and mouse y. Okay, so we start at 1, and then now, oh, I also didn't work. Let's see. I said velocity. Did I say velocity? I meant velocity, meaning that they're not really moving, not position. Okay, run. Okay, see? Now it's being pushed down a little bit. Great. All right, before we move to the next step, why don't we create the faces and the eyes and the mouth? Actually, instead of drawing it using the x and y coordinate at this.post.x and this.post.y, what I'm going to do is I'm actually going to use a translate function to translate the origin point of each of these balls, and then by doing this, I can just draw the ellipse out at 0, 0. And because there are going to be multiple balls, to use these transformation functions, we need to make sure that we use push, which saves the transformation, in this case translate, and then pop, return it back before we call the next ball, so that these transformations don't accumulate. Okay, and the reason that I want to do this is so that it's easier for us to draw the eyes, and then we're going to rotate things afterwards. So for eyes, we're going to use the ellipse function again. And how about we set it relative to the center, right, by the size of the radius. So let's do negative this dot r divided by 4. Y will be the same as the center. And let's do size to be 1/6 of the radius. And that is the right eye. And for the left eye will be same magnitude, but to the right side. Okay, let's see. Run. All right. How about we fill it with the color black? And as you can see, it doesn't rotate. Right? I want it to be able to rotate the eyes. So what we're going to do is we're going to set angle at 0 and angle velocity start it at, let's do 1 actually. And inside update here, we basically just need to update the angular velocity by updating the angle by adding angular velocity. And we're going to be using this angle here. So after translate, we're going to put in rotate by this dot angle. And now it's just moving super fast, too fast. So instead of actually having it move at a constant velocity, what we're going to do is we're going to set it based on how fast it moves in the XY direction. So to do that, I want to set this dot angular velocity. So let's initialize it at 0 and then set this dot angular velocity to increase by this dot velocity of x. So this basically changing the rate of change of velocity, right? So it could increase or decrease over time. So let's try this. Oh, this dot vel dot x. All right. So it moves really fast because the scale are different. So how about we multiply this by, let's do 0.002. Okay, so it's a little bit slower, and I want it to stop over time. So we are going to also multiply it by 0.95. So in each frame, it slows down little by little. Okay, and then let's go back to drawing the mouth. Eyes, and then mouth, we're going to use the arc function to do this. So let's do mouth size as this dot r divided by 6, and you can play around, right? Whatever kind of face that you want. We're going to use the arc function, which takes in 6 arguments. The first 2 is going to be the center of where the arc, of the circle that the arc is being drawn on. So that is going to be just 0, I want it to be at the same x coordinate, right? X axis. And then for y, let's actually also move it down by mouth size. And the arc will be mouth size and mouth size. So it's being moved down a little bit from the center by mouth size. And then basically we're going to draw the size of the arc to have the radius of this much. And it's going to start from 0 to pi. So we have a smiley face. And it didn't work. So there are circles here. Huh. Is this something with the 2.0 or is it me?
A few moments later.
It is me. It is me. Because that looks like the mouth and it didn't go on there. So pop is here. Pop needs to be here. I was about to blame the 2.0, but 2.0 is a good version update, so you should try it. And okay, so we're gonna do stroke to be of the color black, and we want no fill, and we're gonna do stroke weight of size 2. Run. Okay, and next we're going to change the color of the body. So do no fill, and then let's do fill of the color, this.c, and we'll set it right now. So let's put it as another parameter here. And this.c will be equal to c. We're going to be using this color palette. And now we need to, in here, let c to be a random value inside this array, color palette, and then add c as the next argument here. And we want to do that for here as well, right? Then I'm also going to change this to this color. All right, run. Oh, I didn't do no stroke. Let's do body is not no fill, no stroke. All right. The last thing that I want to do is, if I have a bunch of these and then as I click more and more and more, what happens is the array accumulates, but you don't actually see it on here. So let's also write a function called offScreen. So to check if the ball goes off screen, and then we're going to remove it from the array. So offScreen happens when if this dot post dot y minus this dot r. This time it's minus because it's the top, right? The top of the ball is greater than height, or this dot post dot x minus this dot r is greater than width, and this dot post dot x plus, which is the right side of the ball, this dot r is less than 0. Then return true. And inside our sketch here, in this loop here, we're going to call if balls of I dot off screen. If this is true, then we want to remove it from the balls array, and we can use a function called splice, and we're gonna remove that particular index and 1. So this is the function that basically allows us to remove a value inside an array at this particular index, and this is the number that tells it how many from that index we want to remove, and we just want to remove 1. And instead of actually looping it forward, I'm actually going to loop it backward, and this time it doesn't skip any of the balls in the array. So we're going to start from balls.length minus 1, and if it is greater or equals to 0, we're going to subtract it. And how about we here print out balls.length just for you to see that. Oh, if balls.offScreen is true.
A few moments later.
Silly me. I didn't call it. The function was not called. Okay, so we don't need this true either. Now let's move back. Where? Bounds. Let's check bounds again. Run. Also delete this. Run. Now it's 2. Does it go down? Actually, let me just comment this out again, just to show you that now the length decreases as you move. As you create more and more and more and more. Now it works. Let's put back the bounds. Okay, all right. So there you go. And what you can do next is also, instead of using the mouse press here, what if you just have it being added continuously? And we can do that by, what if we do if random, which spits out a number between 0 and 1, not including 1, is less than, let's say, let's do a very small number so that it doesn't crowd out too much. Then we're going to create these. Yeah. And we also don't want to do it inside setup. We actually want to do it inside draw. Maybe this is too small, so let's do 0.1. All right, so just play around with this, okay? Now let's add some typography, and that is exactly why I am using the new version, the 2.0 right now. Not only because it is newly released and I want to try it out, but also because it has some pretty cool features that allows us to do something with variable fonts. First, what you want to do is, how about we come here and we're going to create a string, an array with strings. Let's call it lines, and it is going to say, let's make tech artsy together. All right, and also how to use these new functions. First, how about we go to this website. So this is actually the beta site, so beta.p5js.org, and you can see that my tutorial is also here. Let's go to tutorial and then go to new in p5.js 2.0. We're going to go to this greetings from p5.js 2.0, which is done by Dave Hagrek and Kit Kuxinok. And it looks really cool, but the part that we're going to go to is, we already did this where we changed the version to 2.0. But what I want to show you is this 2D text feature. So first, we're going to load something in this version. We turn up our setup function into an async function, then we can await something that needs to load. Basically, we're going to load the font, and we're not going to be using the original preload feature that we usually do. We're going to use async and await. And I'm not going to go into the details of how that works in this video, but I'm actually going to show you how easy it is to actually implement it. So basically, in front of setup here, we just put in the word async, and then we're going to set a variable called font to be equals to await, and then we're going to use load font. And here they basically tell us that we can just put in the URL. Okay, one thing at a time. Let's go back, and I'm going to create a variable called font, and then inside setup here, not inside, outside setup, we're going to call it async. And then we're going to do what? Font equals to await, right? And then load font. Now, we're going to go to Google Fonts. And basically, you can just pick whatever you want, right? What I'm going to do is, I'm going to show you how to, or where we can get the URL. So let's say that you want this particular one. Go to get font, and you go to get embed code. If you know an easier way, let me know, but this is how I'm doing it. And now what you can do is you can go to import, and basically you just want this URL here from where the quotation starts and ends. So this one here, this part. And I already have the font that I want to use, so I'm going to actually use that. All right, and I click run. It still works. Next, what we're going to do is we're going to first, how about we set text font to be this font here. And then I'm going to set text size to be, let's do 50. And we're going to display the text inside draw here, but I'm actually going to write a separate function. Let's call it display text, and then we're going to call it on top of the balls here. So display text, And we can just use the text function. So this is the same, right? So text, we're going to, actually, I'm gonna write a for loop because we already create that lines array, right? So I'm going to just go through the lines array and then write out each of the strings. So we're going to use the text function. So the first argument is the text that we're going to write. So it's going to be lines of I, right? And then the location, I'm going to put in X and Y here because we're going to declare X to be equals to, let's call it margin, which we'll set. Let's set it now. Let's do margin to be equals to 20. And then Y will be equals to height minus margin. So I want it to start from the bottom here, relative to the bottom, subtract by margin. And then I'm going to subtract it by, so it depends on where it is inside the array, right? So I want, because everything is going to be relative to the bottom, what I want is I want to space them out equally from together here. So we're going to do lines dot length minus 1 times I, and then times the gap that we want for each one, which I'm going to set it equals to font size, actually. Let's call it font size. And, ooh, not this. So it's actually, I did it wrong. So this is how much, where it is, right? So it's actually just lines dot length minus I times the font size, because if not, you can see that the spacing is way too big. Okay, and then let's set the text size by font size. Okay, and then now we can also set the text weight, and I'm going to set it to 300. So the font that I actually chose has text weight from 300 to 800 here, there, yeah. So let's say I change it to 800. Nice, right? But this is no fun. We're in the draw loop, so we should be maybe changing the way it moves. So maybe I set it according to which text it is. So let's do, how about we do T to be equals to, we map it between map I between 0 and lines dot length minus 1. We map it between 300 and 800. Let's set, actually let's call it W. All right, and not only that, what we can do is we can animate it, right? So I'm actually going to use the sine function. And what we're going to do is now, I'm actually going to call this phase, and I'm going to map I between the same amount, and I'm going to map it to 0 and 2 pi, basically have the starting point to be different. And then we're going to set W to be equals to, now we're going to map sine function, and the variable will be T plus W, and T will be how we animate it using the milli function. So the time function basically, and sine spits out values between -1 and 1, right? Sorry, this is phase. It spits out the value between -1 and 1, and we want to map it between the text weight of 300 and 800. And then now we need to set T to be equals to 0 to start with, and then T will be equals to milli. This is the timer basically. And now it moves really fast, so we're going to multiply it by maybe 0.002. Ta-da! Okay, so that probably was super long, but I had a lot of fun making this. And it is super cute, don't you think? I love this tutorial because it actually combines so many of the fundamental concepts from movement to physics to typography to making some animation and what else? So many things and making cute things. So I really hope that you enjoy it. And if you stick around to this point, thank you so much. And I hope that you give it a try.